Well, I just want to remind you, I did send an email out, and if you aren't getting my emails, you need to make sure that you come see me because that means you're not on Blackboard. But I did send an email out to tell you that we're not going to have our quiz today because of the snow day that we had. I guess some of you had snow and ice, but we did not. Um, is that working? Yeah, okay. Um, we're not going to have the quiz today, but we'll have it on Tuesday. And that'll be at the end of class, the last 20 to 25 minutes of class. It'll be short, 5 to 10 questions. It'll be from chapter 1. Normally, we'll take that quiz early on, and so you'll need to read the chapter beforehand. So if you've already read chapter 1 and you want to, you can move on and read chapter 2 if you like. Though we'll be sort of dwelling in chapter 1 for probably another week or so. Yeah, how many of you, if you haven't gotten your book yet, how many is there that actually need copies of that? Okay, I think I can handle that many more. Y'all just see me after class, okay? All right. Y'all liking the book? Y'all read chapter 1 yet? No, you don't like it, or you haven't read it? Okay, that's okay. Make sure you read it by next Tuesday. And the questions will be pretty basic. I mean, they're not, well, they'll be from the text. So if you've read the book, we'll take them pretty clearly from there. I also expect the quizzes to be good practice for you for the exams. So as I go through reading the book, it's my first time to read the book as well, but as I go through, when I come upon big topics, I'll write down questions. And so like I have 20 or 30 questions right now, and some of those are going to go on your exam, and some of them are going to go on your reading quiz. So the reading quizzes are good practice for you. And don't forget the reading quizzes, they don't count a whole lot of points. I mean, they're not insubstantial, but you also get to drop your lowest. So there's some room for failure there in your reading quizzes. All right. When we talked about units last time, remember the system that we use in physics? What's the system of units that we use? The SI system, the international system. And in that, let's see, how far did we get actually? Oh yeah, we got all of them. So length, mass, and time. Length is the unit as a meter. For mass, the unit is a kilogram. For time, it's a second. And then we also talked about the standards for that. And the standard for length is based on the speed of light. The standard for mass is based on a particular cylinder. But then remember we watched that video where they're trying to transition away from that cylinder because it's kind of an archaic standard and move to this, the number of atoms in a silicon-28 sphere of a certain diameter. And that's going to be a more reproducible standard that people can use all around the world. And then the standard for time is the frequency of an oscillating cesium atom. Right? We'll get to charges later on, about halfway through the semester. I'm not going to deal with that now. All right? I do want to do a little bit of stuff with units and what we call dimensional analysis. We'll do some simple algebra. I think it'll help you sort of as we move on. I know for a lot of you, algebra has been a long ways away, perhaps maybe even high school, or some of you have taken it in college, I think, right? Even as athletic training, I'll take some math courses. Okay, so we're going to do some basic algebra. And in the context of dimensional analysis, and you could also see some questions like this on your test, not on your reading quiz because it's not part of the reading, but on your actual test. So dimensional analysis. In dimensional analysis, we're going to look at the dimensions of an equation to determine if that equation is correct or not. So we're going to analyze the dimensions. To determine if the equation is correct or not. Honestly, you probably won't use dimensional analysis for this purpose, ever, but it'll be useful for this course just to get you used to using a little bit of algebra and just dealing with some of these units. So I think it's useful now to look at this. Let's imagine that I have some variables, and I'm going to give you the units. So this is going to be the variable in this column, and in this column I'll give you the unit. So for example, if I have a distance d, I'm going to measure that in what unit in the SI system? It's meter, right? So in the SI system, it's going to be a meter. If you were in the British system, it would be a foot, for example. Let's also look at velocity. V is going to be velocity. I'll write that in parentheses. We'll deal with this a little bit in this chapter. Velocity is a rate of change of distance over time, so it's going to be meters per second. We'll also look at acceleration. This is a rate of change of velocity. How fast are you speeding up or slowing down? That's going to be meters per second, or meters per second squared. And then let's do one more. Mass. What are the units for mass? Kilograms, right. Those are the SI units for mass, or kilograms. Now let's imagine that we have an equation. It can be any equation, really. These are just sort of made up, but using these variables. Let's say that I have this expression, 1/2 a t squared. And I want to simplify the units of that as much as possible. What we're going to do is we're going to put in a unit for each variable. So for example, for a, which is acceleration, I'll put in meters per second squared. And for t, which is time, well, let me do time actually, sorry. So we'll also do time, which is in seconds. So t is in seconds. How does that simplify? If I put in those units, I have acceleration as meters per second squared, and then time as seconds squared. How do I simplify that equation? What are the basic units of that equation? What is it? It's just meters, right? Because the second squared, they cancel. If you write this a little bit differently, you could write it like this: meters second squared over second squared. And the second squared would cancel. And that would give us the units here of meters. Notice one thing that I did not do is I did not include any units for this 1/2, because that 1/2 is a constant and it has no units. Right? Also notice that when t was squared, I also squared the unit. Because if I square time, then that gives me second squared. All right. So that's just taking an expression and breaking it down into its basic units. 1/2 at squared gives me just meters. So then I know that the acceleration times the time squared gives me a distance. Now let's look at this in terms of equation. Can I move on from here? Okay. All right. So let's write an equation. I'm going to have v times t equals 1/2 at squared. And I want to know, is this equation correct? Now, I've already shown that on this side, that has units of just meters. I just replace the a with meters per second squared and the t with seconds, and it gives me basic units of meters. Now I want to do the same thing over here. All right. So let's try that. And I want you to tell me, is that equation dimensionally correct? You'll use your clicker, so go ahead and get those out. And put A for yes and B for no. All right, I'm going to start it. Is it dimensionally correct? That means, do the dimensions on the left-hand side match the dimensions on the right-hand side? Is it dimensionally correct? All right, I'll stop at 50 seconds. 5 more seconds. If you don't know, just guess. What's that? I just stopped it, yeah. So it should say closed on your clicker. Oh, it closed before? Okay, let's see. So more of you put A. A is the correct answer. Let me show you how we did this. Look, I'm going to mark A here as the correct answer, and that means that those of you who got it correct, you get twice the credit when it comes to calculating class participation. But listen, as I told you, I don't want y'all to fret too much over these questions. Just answer them and do the best that you can. If you come to class regularly, I can almost guarantee that you're going to max or get darn close to maxing out your class participation credit. Okay? So the way I do this is I put in units for V, which are meters per second, and then units for time, which are seconds. And then I can cancel out these seconds. And so I have meters on the left-hand side and meters on the right-hand side. And so that checks out that that is a valid equation. All right? Let's get a little more practice. So I think you need a little more practice on this. I know that algebra might be foreign to a lot of you, or at least not familiar for a while, but you'll need it a little bit in this class. So let's practice some more. Let's say that I have is that equation dimensionally correct or not? Don't click in yet. I'm going to, while y'all are doing that, I need to pick something on my thing. Remember, x is in meters, t is in seconds, v is in meters per second, and a is in meters per second squared. Get your answer, just hold on to it for a second. All right, so is this equation dimensionally correct or not? So go ahead and register your answer. Is it correct or not? A, yes, B, no. You will see one or maybe even two questions just very similar to this. I'll give you an equation, ask you if it's dimensionally correct or not. Something similar to this difficulty. All right, I'll stop at 25. So just guess if you don't know. A couple more seconds. All right, looks like most of you put B, which is correct. You're getting the hang of this now? All right, let me show you. We'll do one more after this. But so x is in meters, t is in seconds, so that's meters per second squared, x over t squared. Over here, you have to do something a little bit different. You have to have meters over second, and then you have meters over second squared. When I have a fraction in the denominator like this, I have to write it. I bring it up and flip it. So I have meters over seconds and seconds squared over meters. When I bring that acceleration, I have to flip it when it comes up. My meters cancel. One of my seconds cancel. And so on one side of the equation, I have meters per second squared. On the other side of the equation, I have seconds. So obviously, that's not correct. All right. We'll do one more example. I'll ask you a similar question. Give y'all just a second. All right, moving on. All right, let's look at another example. So let's say that I have distance over time. Try that one. A yes, B no. It's a nice way to start a Thursday morning, isn't it? Dimensional analysis. All right, I'll give you about 10 or 15 more seconds. 10 seconds, I'll stop at 1:15. Okay. Don't worry, we're going to have a little bit more practice. We're about to do a concept test, and there'll be some more questions with this. So here, no, this is correct. This is the correct one. Yeah, it is. Good job, 14 of you. Let me show you. So I have meters per second on this side. All right, that doesn't really simplify anymore. And over here, it gets a little more complicated. So I have meters per second squared, meters per second, and seconds squared, all divided by meters. And now I can cancel out some things. If you want to write this a little bit differently, you could write it like this. You could say meters, seconds squared, divided by seconds squared, seconds. And then this meters comes up and goes right here in the denominator. Whenever you bring something up from the denominator, you have to flip it. All right? Like 1 divided by half, that's equal to 2, right? Because you flip the half when you bring it up. And so my seconds squared cancel. One of my meters cancel. And I'm left with meters per second, which is correct. Yeah, Kayla? Of course, yeah, you could write them all next to one another. Well, like this right here. What did you mean exactly? Oh, yeah, that's fine. Actually, let me write it the way that you did. That's nice. So you could also write it like this. Maybe you'll understand a little better. You have meters per second squared. That's my acceleration. Meters per second, that's my velocity. Second squared over 1, that's t squared. And then d is 1 over meters. I like that. I think that's a lot easier to understand. And then you just cancel out. Our seconds squared cancel out, our meters cancel out, and we're left with meters over seconds. Good, Kayla. Thank you. I think is that easier to understand for you? Maybe we need one more practice on this, okay? And then we will see some more in just a few minutes. So if you've got it, just sit back. But if you don't, let's try this one more. And again, I don't want too much math in this course, but we're going to use some basic algebra, and that's sort of what this is exercising. All right. I go down? Oop, I did go down. All right. Let's see here. Come on in. Is that dimensionally correct or not? If you're still having trouble with these two, remember our class time, it goes on YouTube, so you can go and catch back up there as well. Or if you have to miss class. Stop at 1:15. 1:15. 5 more seconds. Guess if you don't know. Let's see. Not sure. I don't think that's right. A is meters per second. Let's do it the way Kayla said. Meters per second. 1 over the acceleration. I'm going to flip it, okay? So 1 over the acceleration is seconds squared over meters. I'm doing this. I'm saying 1 over meters per second squared. That's equal to seconds squared over meters. Over here I have D, which is meters over 1. And then V is seconds over meters. So I get meters canceled there and there. Oh, it is correct, actually. Good job. Kiss your brain, as they say. You know what that means? Kiss your brain? Who knows what that means? Oh, you aren't kindergartners, are you? Okay, so A is the right answer. If you have trouble with that still, I mean, obviously some of you are still having trouble with it. You can catch back up on this online. Like I said, this is going online. The questions that you'll see on the exam will be similar to these. Or you can come see me, or we're going to have a few more in the concept test right now, okay? Not a whole lot of algebra in this class, but we'll see a little bit as we sort of deal with a few little things. So this is a good way to practice your algebra. All right. Let's keep your clickers out. We're going to do a few more questions just about stuff that we've done. Now, on the clicker questions, first of all, this is for another class. I've made an edited version for y'all, so I'm going to skip a few questions that aren't relevant to you, but I'll have the edited version up on the internet with the answers on them. Okay? So I'll pose you a series of multiple choice questions. And you answer them. This one's very similar to the dimensional analysis problems. I have an equation, x equal a times v, and I want to know what are the units of a in order to make that dimensionally correct. What must the units of a be in order to make that equation dimensionally correct? Well, let's go for 125. We'll do 130. 10 more seconds. 5 seconds. Just guess if you don't know. I know for some of you might think this is a little fast, but it's good practice, okay? These questions aren't worth a whole lot, sort of in the grand scheme of your grade, so it's good practice now to fail on questions so that you do better on the quiz. So if you think it's going too quickly, I understand, but just keep in mind that we're trying to build up some speed in doing these things. All right, so let's see what y'all got. All right, let's see. A lot of you put A, and some of you put C. C is the right answer. In kindergarten, you know, like my little girls in kindergarten, they have a lot of euphemisms for things, like kiss your brain means good job, right? But the one that I like the most is they're going to go for a brain break. Do you know what that is? Does anybody know? Huh? No. It means they're going to go pee in the bathroom. That's their brain break. Yeah. I go to my little girl's class. That's what they call a brain break, which is kind of bizarre to me. But her teacher is excellent. She is the best kindergarten teacher in the whole world. All right, so this is meters. This is meters per second. In order to make this dimensionally correct, I need to get rid of this seconds right here. That means I'm going to put a seconds here. And then that cancels out there and leaves me with meters and meters. So if A has units of seconds, it has to be time. All right? I'm going to skip this. We're not doing any unit conversion. Skip that. All right. Mass, along with what other two quantities make up the three basic quantities used by physicists to derive additional quantities? What was it? You can look at your notes, and you can talk to one another too, by the way, on these questions, if you just don't know the answer, or if you think your friend knows the answer better than you. Or if you think you do know the answer, and you want to share it with somebody, that's fine. Mass, what, and what make up those three basic quantities. Those three standards that we talked about, mass, what, and what. These are good test questions too, by the way. Often I'll just pull questions directly off of this. So this is good practice for you to go through these. Often I say, you know, several questions on your test will be taken from these. We had three basic quantities. Stop at 1:15. 5 more seconds. Guess if you don't know. I'll give you to 1:20. Click in. All right, very good. Length and time. Remember those units for mass were kilograms. Length was meters. Time was seconds, right? Meter, a kilogram's a couple pounds, a little more than a couple pounds. And a second, of course, is... Y'all know how many seconds are in a year, by chance? This is a useful number just to know. Like, you can wow your friends when you go out and do stuff. Because it's a really easy number to remember. The number of seconds in a year is pi times 10 to the 7th. There's no reason that it should be pi, but it just turns out to be 3.14 times 10 to the 7th seconds. So that's about 31 million seconds. That was free this time, so you can share that with your friends if you like. All right, let's skip this. Now let's try this out. Sort of in the, if I have this expression, y equals x squared, which of these is true? So I have y equals x squared. If I double y, what happens to x? Or if I double x, what happens to y? These are two variables. If I double the quantity that's here, what happens here? Or if I double this quantity, what happens here? Or is y bigger than x necessarily? Does it have to be bigger than x? 120, I'm going to stop. 5 more seconds. Oh, no. Don't kiss your brain. All right, that was sort of a curveball. The answer is D, actually. So if I double x, then y quadruples. Well, we're not going to see much algebra. So if I double that, if I double x, I increase it by a factor of 2, that quadruples y. Okay? For somebody that's been saying there's not a lot of math in this course, we've had a lot of math this morning, right? These will go up on the website, yeah. So there's a place there. Yeah, that's a good question. I'm surprised not more people put B. Y is greater than X. Because you know what? If you have Y, let's see this. If I have Y equals X squared, it seems like Y should be bigger than X, right? Because like, for example, if I have 2 squared, then Y is equal to 4. And so that 4 is bigger than 2, right? Y is bigger than X. But what if I had a half, that X was a half? That's equal to 1/4. A half squared is 1/4. So Y doesn't have to be bigger than X. If X is less than 1, Y is actually smaller than X. That's a great question, though. I forget your name. DJ. What was it? Yeah. Hooray. But you prefer DJ? Let me pull out my Facebook. This is my Facebook. You're all in here. Well, all right. Which of the following formulae is dimensionally consistent with an expression that would yield a value for time to the -1? That is, I want to know which of these over here give me units of 1 over s, 1 over seconds. Which of those give me units for 1 over seconds? Oh yeah, I'm sorry. Stop at 205. 205. These are kind of like puzzles. It's kind of like Sudoku. Y'all like to do Sudoku? That's what this is. This is just like Sudoku. All right. Hey, good job. That's right. A is the correct answer. The 20 of you. Good job. Let me show you. So V is meters per second. X is meters, but it's in the denominator. So I have my meters cancel, and I get 1 over seconds. I can do it with these others as well. V squared, that's meters per second squared. Both of them are squared. And then 1 over meters. That cancels and just leaves meters per second squared, so it's not B. C is x over t, that's meters over seconds, so it's not C. And then V squared t is meters per second squared, so they're both squared, times t, which is seconds, over 1. That cancels there and leaves me with meters squared per second. All right, since 1967, the standard definition for the second of time has been which of these? The frequency of the cesium atom, the average solar day, the sidereal day, or Greenwich Civil Time. Of course, you can look back at your notes, or you can ask your friend. But I would expect questions about those standards on the exam. Not on the reading quiz, but on the exam in a couple of weeks, whenever that is. February when? 20th? That's not Valentine's Day, is it? No, that's the 14th, right? That's not far. That's just a couple weeks away. All right. Let's stop in 1 minute. At 1 minute, I'll stop. Excellent. Excellent. It's funny, the second used to be based on the average solar day. You might know why that's not a very good standard for the second? What's that? Yeah, okay. Yeah, yes. The solar day is very difficult to nail down exactly how long it is. It's hard to know when sunset and sunrise exactly are. So it's not as good a standard as especially for measuring very small amounts of time, as the cesium atom, because that's when you can measure that to very great accuracy, and it's also a really small value. Like the cesium atom oscillates about, I don't know, like 10 billion times or whatever in a second. Now, what's the standard for the meter? Most of these, by the way, have been a standard for the meter in the past, but what is the current standard for the meter? Stop at 45 seconds. 45. Excellent. Yeah, it used to be that there was a bar in France, like a metal bar, not like a, like a bar. So like a metal bar, and they said that is a meter. And then before that, it was a fraction of the distance from the Earth's equator to the North Pole, which just like the solar day, is very difficult to measure that distance from the North Pole to the equator. You don't really know exactly where the North Pole is. You don't know exactly where the equator is. It depends where you measure it from, right? You're going to go over mountains and all that jazz. So, but they used to base the meter on that. Oh, let's not do this anymore. Let's get that. You want it? Well, now you know the answer. Okay, let's not doing that or that. The speed of a boat is given in knots. That's a nautical speed. If a speed of 5 knots was expressed in the SI system of units, what would it be? This is a speed. What would the units be in the SI system? The speed, or that's the same as velocity. Stop at 50 seconds. About 5 seconds left. Excellent. Yeah, I want to do another one. Okay, let's practice it one more time. Which of these is not dimensionally correct? Well, I didn't want to spend so much time on this, but I think y'all still need a little practice. Which of these is not dimensionally correct? So remember, you're going to write in the units for each. I'm just going to set up A for you. Just seconds for time. X is meters. You can write it over 1 if you want. And this is meters per second. And then you would cancel out all the like terms and ask yourself, are those two equivalent, the units on either side? So obviously for A, they what? Are or are not equivalent? No, they're not, because you have seconds, meters squared over seconds. So the answer is not A. Oh, I'm sorry, guys. I actually, we're looking for the one that's not dimensionally correct. So what is that answer? It's A. I'm sorry. Did I confuse you? Yeah, so the answer is A. So go ahead and click in A, okay? I'll give you a few more seconds to click in A. That is the correct answer. Yeah. Oh, yes. I'm sorry. I just did it wrong. Okay, it's not A. Thank you, Destiny. Destiny, right? Yeah. Gosh, I'm just confusing the heck out of y'all, right? So, yeah, so A should have been meters and then seconds over meters. So that is dimensionally correct. All right. Well, let's go back. It's not A, in fact. It's one of the others. Yeah. You're looking for the one that's not dimensionally correct. All right. Looks like most of you have an answer in. I'll stop at 345. Okay, let's see. Is C not dimensionally correct? Let's see. I have meters per second. And then acceleration is meters per second squared. And then 1 over seconds. Yeah, so that is meters per second cubed. So that is not dimensionally correct. C is correct. All right, looks like y'all sort of have that down, right? That's really boring, I know. And you're not actually going to see it a whole lot out of this first chapter, but it's useful to sort of practice those algebra skills. Because they will impress your friends. Like if you go and show them how well you can do algebra, they shall be impressed. Okay, good. That was tough. I'll put this up, the edited version with just the questions that we did in class on the website. Just to remind you, you go to the website, which is linked from Moodle. Well, it'll be in another thing down there. I haven't put in the link yet, but it'll say concept test, and you just click there, and you'll find the chapter. All right? All right, let's move on to Newton's laws. So most of that stuff was not in the book, and now we're moving into stuff that is in the book. So if you've read the chapter already, hopefully a lot of this will just be, oh yeah, that's what he was talking about. But we're going to first watch a little video about Newton's laws. This is from the Veritasium. I showed you a Veritasium video last time. Don't y'all love that channel? Y'all watch it? The Veritasium channel? It's a really cool channel. Yeah, he has a lot of cool stuff. It's not just physics that he goes into, but give me just a moment here. Log on to my email. All right, so let's look at the laws of motion. There are 3 laws of motion. Mostly they'll be qualitative, though with one of them we'll have a simple equation. All right, so the first law of motion, this is often called the law of inertia. You might recall what he said was the first law of motion, that objects will tend to what? They'll tend to stop, right? And the reason that people think that, and people in Newton's time thought that, Aristotle, who was a predecessor to Newton, had this idea that everything has this natural state, and that natural state is to be at rest. And the reason for that is, it seems obvious, right? You look around, and most things are at rest. Most things are at rest. So it seems obvious then that that's going to be the natural state. Like all of y'all are at rest, more or less. If you look outside, most things are just sitting there. And so Aristotle said that is the natural state. Aristotle also said further that in order to take something out of its natural state was like this violent tearing it away from that state. And he sort of looked at it in not just physical terms, but also in this sort of ethereal, spiritual terms as well. But Newton came along and said that's not true, and he came up with this law of inertia. He said that an object at rest, or an object will tend to stay in its state of motion unless acted upon by a force. Right? In your book, there's a slightly different retelling of that, but it's the same law, that an object will tend to stay in its state of motion unless acted upon by a force. That means not only if it's at rest, then it will tend to stay at rest, but also if it's what? If it's in motion, right? So also if it's moving. So if you're moving along, you're not going to stop unless a force acts upon you. I know you're all getting sleepy. It's been a long time. Don't worry, we only have about 30 more minutes, right? Won't get at 10:30? No, they changed the schedule this semester. This class goes until 10:30. I'm pretty sure. What? Right. Yeah. Okay. Yeah, so that's the law of inertia. Now, when we talk about inertia, inertia is or mass rather, is a measure of inertia. All right, so mass is a measure of inertia. Remember, the units for mass were in kilograms. And it basically says that if you have a lot of mass, then you're going to tend to stay in your current state of motion. You'll need a larger force to act upon you if you have a larger mass. So mass is a measure of this inertia, a measure of this tendency to stay in your state of motion. So if you have a lot of mass, you have a greater tendency to stay in that state of motion. Right? If there's a train coming at you, you're not going to jump in front of it, right? Because it has a lot of inertia. And so it's going to be very difficult to stop. All right, so that's inertia. I have another little video. This is also Veritasium. They have a lot of cool stuff about Newton's laws. You want to watch that? It's kind of fun. It's not irrelevant either. It's interesting. All right, let's look at the second law of motion. The second law of motion, which is called, the book calls it the law of acceleration. If you remember in the video, the incorrect laws of motion, he said that the force, if you apply a force to an object, that's equal to the mass times the velocity. So if you apply a greater force, that causes you to move faster. And that seems true, but it's not entirely true. It's not really true at all. The law of acceleration says that the acceleration of an object and let me define this quickly because we haven't done that exactly yet. I said earlier that the acceleration is the rate of change of the velocity. So the acceleration is going to be our velocity divided by time. It's how quickly do you speed up, basically. If I'm accelerating, how quickly does my velocity change? And it's equal to my velocity over my time. It is the rate of change of velocity. So they're related, but they're different. And in the law of acceleration, which is Newton's second law of motion, he says that the acceleration of an object is proportional to the force. We would write this mathematically like this. We would say that the acceleration is proportional to the force. That means if the force goes up, the acceleration is also going to increase by the same amount. So if I double the force, I double the acceleration. Right? So the acceleration of object is proportional to the force. Did I spell that correctly? No. No. And inversely proportional to the mass. So the acceleration is inversely proportional to the mass. That means if my mass goes up, my acceleration will go down for a given force. So I can put those together and I get the law of acceleration in equation form. It just says that A is equal to F over M. A couple things about that. The force here is something we call the net force. Force, well, first of all, a force is a push or a pull. I had that in even second grade, what a force is. In the British system, what do we measure force in? What, sorry? It is weight, yeah. Pounds, right. So a force in the British system is measured in pounds. In the metric system or the SI system, we're going to measure it, which are going to like this, in newtons. Y'all know why we call it newtons? Because of Isaac Newton, right? Yeah, and that's abbreviated as a capital N. And in particular, net force is just the sum of all the forces. All right? Here we go, just a second. I'm going to move on to the next page. Let's show you what the net force is, and then next time we'll pick up with Newton's third law. But I have another little assignment I want you to do before you leave. since y'all just shaved like 10 minutes off my class time. All right, can I move on to the next page, y'all? Okay. All right, so the net force, the sum of all the forces. There's some examples of this in your book in that physics of the human body. Let's say I have a car or whatever. I think this is the example they use. I have a car. When I was a kid, we were pretty poor, and we would run out of gas a lot. My wife, she doesn't really understand this. I tell her that running out of gas, like that's, I always remember very clearly when I was a kid and we would run out of gas. So that's a good thing. Like those are memorable times to run out of gas. And so sometimes I try to get her to push on without getting gas. But no, if we run out of gas, that will be memorable. But anyway, so we'd run out of gas and then you have to push your car, right? And let's say you and your brother, this is me, and then my big brother, Tony. And we had to push the car, and our mom or dad is in here. Push, push. And we're pushing the car. And let's say Tony, he's quite a bit older than me, so he pushes with, I don't know, 300 newtons. And then I push with a force of 100 newtons. Then what is our net force? It's the sum of all the forces. It's 400 newtons, right? I have 300 plus 100 newtons, so that's equal to 400 newtons. All right? Well, let's say, like my mom was taking us to school, because I remember one time we ran out of gas on the way to school, and we had to stop at the forestry service, and they had some gas, fortunately. But my middle brother, Joey, hated to go to school. In fact, one year, it was like his 10th grade year or whatever, he went to like half the days. He skipped half the days of school. You go to jail if you do that now, but he skipped half the days of school. He dropped out after that year. But so Joey says, I don't want to go to school. So he stood over here, and he pushes back with a force of 200 newtons because he doesn't want to go to school, right? Because me and Tony are trying to get to school. Joey doesn't want to go to school. What is the net force in this case? 200 newtons. Very good. So the point being here is that when we do a net force, we're dealing with vectors here, and vectors have direction. And Tony and I are pushing in the positive direction, and Joey is pushing with a negative direction. So if I want to do the net force here, it's going to be 300 plus 100 minus 200 newtons. And so that's 400 minus 200 newtons, which is 200 newtons. So with all of these, the net force, which is the sum of all the forces, this is just a summation symbol. It just means that I've added up all the forces, is equal to 200 newtons. 300 plus 100, which is 400 in the positive direction. But then Joey, who doesn't want to go to school, is pushing in the opposite direction to try to stop the car. Is he pushing hard enough to stop the car? No. My mom always won. He usually went to school. All right? So that's a net force. Mm-hmm. That's right, yeah. Yeah. We'll deal with that later. We're not going to get into negative forces so much. Okay? Take out a sheet of paper. We have 5 minutes left. I just want you to sort of introduce yourself to me. Just want you to write your name, your major or whatever, but then also something that you find interesting about yourself. Okay? And then you can hand it in on your way out. Your name, your major, and something interesting about yourself. And then just hand it out on your way out. Hand it in on your way out.